This video, we're going to start looking at limits. And what are limits and how do we use them? How do we apply them for our purposes? So this animation is showing here that we're approaching some number. 1 is our input. And the black dot is moving from the left, and we're approaching something to get to a particular value. And it looks like as we get closer and closer to 1, the y-coordinate is getting closer and closer to 2. Doesn't actually get there, but it gets pretty darn close. So that's a basic introduction of what a limit actually is. It's about the intended height of the function. What is it actually going to do? But we've actually looked at what happens from the left-hand side. What we're going to look at next is what happens from the right-hand side, and does that really change anything for us? So as we're approaching this value, x equals 1 still again, from the right-hand side, you notice it's not exactly approaching the same thing. It's actually approaching 3, so a little bit different value. So we're going to say then that the right-hand limit approaches 3. The left-hand limit approaches 2. So the limit itself doesn't exist. In order to have a limit exist, the left and the right have to approach the same number, and this is not exactly happening here. So we're going to get to some examples and clear up some things here in just a second. There we go. So limits, intended height of the function. Now that the animation was showing you that we need to come from the left and from the right and to approach that same value in order to make it work, to have a limit. So we're going to look at some examples here. The notation here is going to say lim. That means limit. In other words, what does this function want to do as we approach -3? And we've got to approach it from either direction to be able to get that same value. If we don't get the same value, then we have a little concern. So as I'm approaching -3, so -3 is this value right here. So I'm going to make a little notation here, just because I know that's what I'm looking for. As I approach from the left-hand side, so from this direction, I'm getting closer and closer to -3. It appears that my intended height is 3. But then I want to test the right-hand side. So starting in this piece, moving from the right towards -3, I approach that same value. And so that's my limit. The intended height of the function is to reach 3. Whether it does it or not doesn't make a difference. The left and the right are approaching the same y-coordinate as we get towards -3. On the second one, we're going to do the same basic idea, but now we're looking at the limit as x approaches 0. So 0 is this guy right here. So something weird going on here. If I start to the left, so there's nothing over here in the left, I'm going to start here in this piece. We're getting closer and closer to x equals 0. The y-coordinate gets close to 0. But from the right-hand side, when I drop down here, I'm actually approaching a different number completely. And it doesn't matter that it's defined here, but it's not defined here. It's about making sure that the function is approaching the same y-coordinate or output from the left or the right, and it's not. So what I'm going to say about that limit is it does not exist. Oops, I can spell does. That would be very helpful. Does not exist. And a lot of times they'll write that as D and E. Does not exist. As I approach 1, 1 is this guy right here. Coming from the left, it looks like I'm approaching -1. Coming from the right, I approach -1. And so that is my limit. If we look at 3, 3 is this right in here. Approaching from the left, approaches 2. Going from the right, also approaches 2. You might say, well, wait a minute, what's that big open dot there? Well, that's a hole in the graph. And that has really nothing to do with limits. Limits are about intended behavior of a function. It's not about what it actually does. So even though those are holes in the graph, the function intends from the left and the right, as we approach 3, to equal 2. Whether it does or not is insignificant. It wants to. Whether it does or not doesn't make a difference. So that's looking at graphs. The other part we're going to look at is piecewise functions. And piecewise functions are going to be a little bit more complicated than a graph because we don't have a picture to look at. We just have a function written in several different pieces. So this particular function is defined in 4 pieces. We have negative x minus 1 when x is less than negative 2. It's defined as 1 when x is greater than negative 2 but less than 1. 5x minus 4 when x is greater than 1 but less than 3. And 2x plus 1 when x is greater than or equal to 3. So for limits, what we're looking to do is figure out, as we approach these numbers, what's going to happen. So the first thing we're looking for is 0. And 0 fits conveniently nicely in this region here. So if we have a piecewise function, and these are all linear pieces, so that's actually really, really good news for us. If it fits directly in one of these regions, all we need to do is take that number and evaluate it, plug it in, and see what you get. If we were to graph it, we would see that the intended height from the left and the right would be equal because we're talking about linear pieces. So at 0, since it's in this region, plugging it in, I'm going to get 1. The limit equals 1. And we have a similar one here at this one, limit as x approaches 2. 2 fits conveniently in this region here between 1 and 3, and so I can take 2 and plug it into there. Plugging in 2, I've got 5 times 2, which is 10. Take away 4 gives me 6. That's the limit of the function. The remaining ones are ones where we have values where the function is changing. So at negative 2, at positive 1, and at positive 3. This is where the difficulty steps up a little bit because what we actually have to do is consider the left and the right. So when we have negative 2, because it's switching here, we actually have this left function and this right function. And what I'm trying to do is see if they give me the same results. If they give me the same results, then that tells me that the function will have a limit, and whatever that value is the limit. If they don't equal the same thing, the function does not have a limit at that particular value. So when I plug in negative 2 to the top one, I'm going to take the opposite of negative 2, which is 2, and take away 1, and I get 1. From the right-hand side, I'm going to plug negative 2 into, oh, it's just 1. So the left-hand limit was positive 1, and the right-hand limit was also positive 1. Because the left and the right are exactly the same, that is my limit. When I go to 1, the left piece would be this one here, and the right piece would be this one here. So the left, when I plug in 1, I get 1, the constant function. From the right, when I plug in 1, I get 5 times 1, which is 1, take away 4. I get 1 again. So the limit is 1. And here's where it gets a little bit strange. Did you notice that at 1, the function's not defined? That actually doesn't matter for us because we're looking about intended limits, intended height of the function, not whether it actually is defined there or not. And what this would look like on a graph, if we were to graph these 4 pieces, is at 1, we would have a big open circle, a hole in the graph. And so the last one here, we're going to plug in 3. So when I take 3 and plug it into the leftmost function, so 5 times 3 is 15, take away 4, I get 11. When I take 3 and plug it into the bottom one, which represents the right approach, I'm going to take 2 times 3, which is 6, plus 1, I get 7. And 11 and 7 clearly are not the same number. So as we approach from the left, we're going to approach 11. From the right, we approach 7. We're not approaching the same thing, so there is no limit. And we're going to say that that does not exist. Again, key idea from this section, whether you're looking at a graph or piecewise function, limits are intended heights of the function. And the intent has to be the same whether we go from the left or from the right. It can't be one or the other. We're not going to pick one or the other. We're going to approach from the same direction. Let me clarify, not from the same direction, but from either direction, from the left or the right.